Welcome to the Nanovation podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com.
The ones that succeed are the ones that are answering their own questions. The questions that they think about when they're running or when they're watching TV or in the shower or whatever. And they get ideas for it. So I didn't realize when I was younger that science really is about following your own curiosity and trying to figure out for yourself what is it you'd like to learn about the universe.
That's Daniel Whiteson, a professor of physics and astronomy at UC Irvine, talking about the importance of following your curiosity in science. In this fun, freewheeling 50th episode of the Nanovation podcast, Daniel and I talk about the connection between LEGO and particle physics, how the cell phone in your pocket can detect high-energy particles that physicists don't even think should exist, and the role of nanotechnology in the discovery of the Higgs Boson. We talk about Daniel's remarkable outreach and communication efforts, especially those in collaboration with his friend and colleague, Jorge Cham. These include the podcast Daniel and Jorge Explain the Universe, the book We Have No Idea, A Guide to the Known Universe, and a new kids show launching in 2020 on PBS called Elinor Wonders Why. Daniel has a rare ability to marry technical depth with clear language and humor. This episode is a real treat. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. So it's a pleasure today to have Daniel Whiteson on the show. He is a professor of physics and astronomy at UC Irvine over on that other coast. He works on probing the structure of matter and trying to understand the nature of its interactions at the various smallest scales, most likely smaller than nanometer scales, with the goal of understanding the fundamental nature of our universe. And he'll talk more about that. This is a bit of a different episode because Daniel doesn't explicitly work on nanoscience, but he has worked on some really interesting projects as well as science communication, and so we're going to talk all about that. So Daniel, welcome to the show.
Thanks very much for having me on. It's a pleasure to be here. And you're right, we don't work on nanoscience. In my field, nanoparticles are way too big for us to even consider.
Enormous.
Yeah, exactly.
So if you read, you do, the least amount of research you can possibly do before a podcast to find out about someone like Daniel. You'll go to his website at the UC Irvine physics department, and you'll learn that he does a lot of work with the Large Hadron Collider in Switzerland. That's where the Higgs Boson was discovered, and I was hoping you could briefly overview for folks what generally the problems you're interested in and a little bit about the work you do.
Sure. I'm assuming that was a hypothetical scenario where somebody only did a few moments of research before podcasting, not the reality.
Very hypothetical. Exactly. It's extremely hypothetical.
All right. Well, in that hypothetical situation, the goal of our research, as you said, is, a pretty modest one, which is to understand this crazy, beautiful universe that we find ourselves in. The universe has all sorts of weird stuff in it. There's people, there's cats, there's hamsters, there's stars, there's dark matter. And our question is, how do you get all that stuff? How do you make all this stuff? How do you understand all these different kinds of crazy things living together in the same universe? And the idea is maybe it's all built out of the same little bits, right? Like maybe we live in sort of the Lego version of the universe where you can make all sorts of different complicated stuff using a bunch of tiny little pieces. And, you're familiar, of course, with the periodic table that tells us that everything you've ever touched or tasted or eaten is built out of the same elements. And so we already have a clue that the universe is sort of organized according to this Lego principle. And what we're doing at the Large Hadron Collider is trying to push that as far as we can. We're going inside those elements and seeing the quarks and the protons, and going inside those quarks to see what those are made out of. And our fundamental goal is to discover sort of a minimal set of objects, the smallest set of Lego building blocks out of which you can make everything.
And that's pretty much been the goal of physicists for a while, continuing to look and see what is ever smaller that is a component of everything. Do we have any sense for how small we can go?
Well, that's a great question. First of all, I want to comment on your suggestion that that's sort of the overriding goal of physics. It's definitely the goal of my subfield, particle physics. We're like diving deep into the core of the onion there. But I think it's fascinating in science how you can basically stop at lots of different levels, of that onion, and there's still fascinating puzzles, and the science still works. Like there's a huge amount, obviously, of interesting stuff at the level of the periodic table, right? That's the whole field of chemistry. And there's amazing questions there. And you can even find pretty simple mathematical descriptions. And so to me, it's incredible that, first of all, that science works, that the universe can be described by physical laws that can be expressed in mathematics we can understand as humans, and that the sort of emergent phenomena at various levels can be described by pretty simple mathematics. So that blows my mind every time I think about that. Like, why is the universe understandable at all? And why is it understandable at all these different levels? But you're right. In my field, we're going for the center of the onion. We want to see things at the smallest scale. We do have some ideas about whether there is like a smallest scale, whether things go on forever. Though that's like one of the deepest philosophical questions. Is there eventually even an answer to this question, or will we be going on forever? And on one hand, I want there to be an answer because that would be so satisfying. On the other hand, that would sort of mean the end of this intellectual inquiry, right, around which I based my whole life.
Well, what you really want is, to finish it right around when you're 65 or 70 and then mic drop and then walk off, right?
Exactly. Sorry, folks, we used up all the science. No, we finished the end of this rich vein of physics. We do have a clue that there is a light at the end of the tunnel, but the tunnel is really, really long. And the clue is also pretty indirect. We know from quantum mechanics that things can't be well-defined arbitrarily small. Like quantum mechanics tells us there's a fuzziness in the universe. And this means that there's like a lack of information. It's not like things are happening at every scale, at every tiny distance, and we just don't know them. There's really a fundamental randomness and lack of information about what's happening in the universe. And you can try to estimate from basic quantum mechanics, like what is the smallest distance that has meaning, right? Like what is the smallest distance where you could divide it in half and have that number mean something, where you can know things at a smaller scale. And to do that calculation, it's really hand-wavy. Basically, what you do is you find a bunch of constants of physics, like the speed of light and Planck's constant and the gravitational constant. These numbers that have just sort of fallen out of physics over the last couple hundred years. And you combine them to get something in the units of meters, right? Just like, this one has this units, that one has those units. Can we rejigger them and square root them and whatever so we get a number in terms of meters? And and we do that, and it's called the Planck length. And it's a really small number. It's like 10 to the minus 35 meters. So, yeah, it's pretty small. And that's not a great argument. It's not like, wow, we derived the pixel size of the universe. It's just like...
I was going to say, you convinced me, though.
Well, it's sort of like, this is the only thing we can do, and also the dumbest thing possible. But because we don't have any other ideas, the dumbest thing possible is also the smartest thing so far. And so it's a reasonable, it could be off by a factor of 10 to the 5 or 10 to the 10, but it gives you it's like an order of magnitude of the order of magnitude, right? And it might be right. It might be that there is a smallest distance. It would make sense quantum mechanically for there to be a smallest distance. And so we're pretty far away from that. The smallest thing we've seen so far is like 10 to the minus 20 meters. So we're 15 orders of magnitude away. So there's plenty of juice left in particle physics for people to discover stuff.
This next question is probably, you might roll your eyes at it a bit, because I feel like it's similar to when a band gets asked to play their greatest hits.
Okay, I'll prepare my eyes for rolling. Go ahead.
Okay, prepare. And so one of the things that has gotten some press that you've been part of in the last couple of years has been this thing called CRAFIS, or cosmic rays found in smartphones. Yeah. So could you talk about that a little bit?
Sure, and I'll let you know I didn't roll my eyes because I thought you were going to ask me about whether the Large Hadron Collider was going to destroy the world with a black hole. So I'm grateful to talk about CRAFIS instead.
We can. That's it. That'll be in the lightning round. I'll save that.
All right. Yeah, this is really fun. My research group focuses on particles in beams. So we smash protons together, try to figure out the nature of matter. But we work in really big collaborations, like 5,000 people at a time. And one of the challenges in working in a big collaboration is that sort of the creative direction of it is set at the very top. And that means that if you're a graduate student, you don't really get to like design the experiment or come up with new ways to do science. You just sort of jump on a big moving ship and, you add your oar to 5,000 other slaves. So I have this exercise in my research group every 6 months or 9 months where everybody has to come up with a crazy idea for a new experiment. And there's no limitation on cost or practicality or whatever. Just like, it's practicing creativity, scientific creativity. Like, what's a big question? How could we possibly answer it if given $1 gajillion and a gazillion years? And at one of these meetings, one of my students came up with an idea that maybe smartphones, because they have these CMOS devices in them, which are basic little particle detectors, maybe smartphones could see particles. Like particles coming from space, cosmic rays, these particles that come from the sun and penetrate our atmosphere. And funnily enough, at the same meeting, I give myself the same assignment. I had the same idea. So at this meeting, we were both, whoa, look, we both suggested this crazy idea that maybe phones could see particles. And so then we thought, all right, let's figure it out. Could this actually work? And we figured out the physics pretty quickly. It turns out that your phone does have a little CMOS device, which is sensitive to particles, like a muon that comes through the air will leave a little trail of electrons and holes through the silicon. And we know that stuff really well because we use that physics at the Large Hadron Collider to actually detect the passage of particles. So we figured out that phones could see individual particles, and that was really fun. Then we spent the next few weeks writing a little app to prove it to ourselves. And that was the first app I ever wrote. So that was a lot of fun. And then we wanted to know, okay.
So real quick, before you ask that next question, how do you tell the different particle types apart, real quick?
Yeah, you can't.
Do you need to do that? You can't. Okay.
All you can tell is that some sort of ionizing particle, something that feels electromagnetism, went through the device. It could have been a muon, it could have been a proton, it could have been some ionized nucleus. Could have been a high-energy photon. You can't tell. The only data you get is the image, right, which just tells you about how much energy was deposited, which is proportional to the number of electrons read out per pixel. So it's pretty coarse information. But it turns out there's some really interesting open questions in physics that this might help answer. And one of the really interesting open questions in physics is, where are cosmic rays coming from? A lot of them come from the sun. But a lot of them don't come from the sun. They come from other galaxies and other crazy places. And the amazing thing is that some of these cosmic rays, remember they're just particles, have ridiculous amounts of energy, 10 to the 20 electron volts of energy, which is thousands or millions of times more than the energy in the beams at the Large Hadron Collider. So something out there is basically a huge particle accelerator, and these particles come to Earth, and there's no natural explanation for them. You ask astrophysicists, what's the highest energy particle you expect to ever see anywhere in the universe, ever? And, they take a particle and they slingshot it around a black hole and a supernova, and they're still off by a factor of 1,000. So there's these particles shouldn't exist, but they do. And that's fascinating from a science point of view because it's a clue, right? It's well, there's something weird out there. Maybe it's some weird kind of star. Maybe it's alien particle physicists shooting their accelerator at us. Who knows? So then the question we were asking was, how could we use these phones to maybe see these particles from outer space? Because the biggest problem is that they come, but they're kind of rare. And so you need a lot of detectors in order to see them. And so we thought, how many phones would you need to sort of tie together into a global system in order to see enough of these things to do real science. So there's a telescope down in South America, cost $100 million to build, and it's 3,000 square kilometers to capture these cosmic rays. And we thought, how many phones do you need to tie together to sort of equal the science power of the state of the art? And so we did a bunch of calculations and simulations, and frankly, I thought the answer was going to be like 5 quadrillion, and it was going to be impossible. But we did the numbers, and it's about 5 million. And we thought, wow, 5 million, that's kind of a big number. It's like more than I could purchase with my research funds. But it's a tiny number compared to the number of phones on the Earth. There's like 1 million phones turned on every day. There's billions of phones out there. There's billions of phones that people aren't even using. They're just like in drawers somewhere.
Yeah, I mean, you can assume, several billion people are using a phone on a regular basis around the planet.
Yeah, exactly. So then we thought, well, that's actually a pretty small fraction of the population. So then we thought maybe this is actually doable. So we got a tiny little bit of funding from somebody here in Orange County who thought it was exciting. And the last few years we've been working on making this app real, robust, scientifically calibratable, and developing the technology. So it's been a lot of fun. We still don't know if we're going to be able to do this, if we're going to be able to make the phones. There's a lot of challenges there, like have the phones running, have them not overheat, have them not draw too much battery power.
Is this the kind of thing where you would say, run them at night? They're just sitting on someone's nightstand and you hope it happens at night?
Yeah, exactly. But the issue is, it uses the camera because that's, the device. And we don't actually want to see the insides of people's bedrooms at night. But it's a little weird to say like, hey, I'm going to turn on the camera in your bedroom at night and upload the results to the internet.
Right.
Yeah. So there's a lot of stuff to figure out there, and we want to get it just right. So we've been working, and we have a very small team. So we've been working in beta for a few years to try to really polish this thing and make it work before we try to go big and really get a big user base.
When I first heard about it, it reminded me a lot of SETI. Right? SETI was that from 20 years ago, that distributed search for extraterrestrial life on using people's processors when they were in kind of screensaver mode to do a bunch of calculations, I guess, on telescope data to try and see if there's anyone trying to talk to us. Do you remember that program? Yeah,
absolutely. And I love that. Okay. And because people feel like they get to contribute a little bit, right? Like they're participating. And I think that's really exciting. I think a lot of people out there would love to be part of a big project, to discover something new. And that's what we want to tap into also. We want people to feel like, hey, you can be part of this. You can be an astrophysicist. You can help see these particles from space, and maybe we can help figure out where they're coming from and what or who is sending these particles to us.
Yeah, and I think we'll probably see a lot more of this in the coming decades as sensors become much more widespread and we're all carrying these things around with us and the computational power gets better. I want to point out one thing that I love about this idea, and that is that I view it as really elegant process innovation, where normally folks use really expensive localized telescopes to try and do this. And you're just inverting the problem, basically, and saying, let's put it and distribute it. And it's a really innovative change in the process of detecting particles from outer space. And if it works, it's remarkable what it might be able to provide you for a much lower cost.
Yeah, and it's a sunk cost, right? Like consumers have spent billions and billions of dollars on these smartphones, right? Mostly to play games and message each other. It dwarfs the science budget of the United States. And so our thought is like, well, we can't build that ourselves, so let's just piggyback on what already exists and see if we can reuse it to do some interesting science. I wish that people thought fundamental science was as important as having a faster smartphone, because the funding priorities in this country that we make are totally out of whack, if you ask me.
We should come back to that. That's a great thing to discuss, especially because we have someone in you who really does do fundamental science, and I think I do not. I do I think innovative process science and try and do new things that way. But there is interesting questions about allocating funding towards fundamental science, and even maybe what I'll call fundamental process science as well. So maybe we'll come back to that if we have time on the end. So you'll have to come back and let us know whenever you've detected these so-called, what are they called, ultra-high energy cosmic rays, for lack of a better term, because you don't really know what they're coming from.
Yeah, it's been a mystery for decades also.
So, since this is a podcast about nanoscience or nanotechnology, I think it's important, as loosely as we can, to connect the discussion to some aspect of that. And so I was hoping you could talk about one thing, even though it's orders of magnitude larger than you like to deal with or usually deal with, something where nanoscience or nanotechnology has enabled the work that you do on these smaller length scales.
Yeah, actually, I think the connection is not much of a stretch. I think there really is a pretty natural idea there. And remember, for your listeners, that what we're doing is we're smashing these particles together, and we start with protons. And the scale of protons is like, less than a femtometer. So we're talking about like, a million times smaller than a nanometer. So it's really pretty small stuff. We smash them together, and then particles fly out. And really the science that we're doing after that is basically take a picture of what comes out of this detector, what comes out of this collision. And so we have these particles that fly through. We want to get their trajectories. We want to get their direction and their energy. And essentially it's about taking a really high resolution image. Now, how do you take a picture like that? We don't just have a camera. What we do is we try to sense the passage of these particles. And in the last 20 or 30 years, something that's really revolutionized our field is the ability to use silicon detectors to image the passage of particles. This is a nice connection, actually, back to Crayfish. We print, silicon, little strips of silicon that when a particle passes through, it knocks out some electrons, and it creates a little voltage gap, which we can then read out. And the only reason that we can make silicon at a fine enough resolution to give us the kind of pictures we like is because we're piggybacking off of nanotechnology and the whole industry there that's been focused on printing smaller and smaller circuits for computers. So this is, again, another time when we're trying to surf off the back of the massive consumer electronics industry. And so silicon lithography, this ability to print like nano pictures of silicon in these configurations, allows us to basically print a camera. Right? It's like a detector that's like a camera to tell us really precisely where the particles went.
So are the pixel sizes similar to what are in cell phones, or is that a custom design in terms of the pixel size?
No, they're a custom design, and we try to get them as small as possible. And we're also constrained by funding, of course. And so for a long time, all we did was sort of 2D. We had these long strips, like, much, much longer on one side than on the other, really long rectangles. And that would give us, a sense in or 2 dimensions where the particles passed. And then we would overlay them at different angles so you can get sort of a 3D trajectory. But then more recently, we started doing actual pixels. And so we bump on a little piece of silicon to the readout system and get them as small as possible.
I'm curious about then the size of the overall detector, like at the LHC. What, in terms of dimensions, if I were to walk up to it, is it something I can hold? Is it bigger than that?
Oh, no, the entire detector, including all of it, is about 40 meters by 40 meters by 40 meters. So it's like like the Borg ship. It's like this huge thing of electronics. And so it's way too big. But most of the volume is just these outer bits where they're the calorimeters. These are the parts that try to slow down the particles and extract their energy. So they have to be really thick layers of material to slow down these really high energy particles. The stuff at the center of it, at the core, this is where the silicon comes in, is much, much smaller. This is the kind of thing, it's like the size of a small car or something.
Much, much smaller. Size of a small car. I asked the question because my lab is interested in scalable nanomanufacturing. So how you can produce, let's just call it kilograms of those little diodes, right? And then, of course, the assembly and integration in an application like this is also an enormous challenge. But most of the processes we've developed over the years out of the silicon industry are just not really scalable unless you have that gajillion dollars to build that detector the size of a small car. But there's lots of other applications that you'd love to have a detector that might be the size of a wall, but the just cost is exorbitant for lots of commercial things. So if you think differently about the processing of those photodiodes, there may be new application spaces that we can open up.
Well, the smallest that we've achieved so far is 10 microns or something like that. It's the smallest, the finest resolution so far on silicon pixel detectors.
Right, and there's the pixel size, and there's the overall size of the detector.
Right.
And so pixel size, okay, we can let's say we can do that. But in terms of applications where you want an enormous area and don't have a gajillion dollars like you might have to build the LHC detector, I know you want more money still, but
hey, can I have another gajillion? I mean,
I'm doling out gajillions left and right. Yes, of course.
I wonder what a gajillion dollar bill looks like.
And the zeros are wrapped around the backside.
Maybe the first bill with scientific notation on it. That would be cool.
Well, that's really cool, and thanks for connecting your work to the themes of the podcast. One of the things I was really excited to chat with you about is the great work you're doing in what I'll broadly call outreach and communication. So for those who don't know or haven't read the show notes yet, Daniel has been doing a number of things in the last couple of years. One, he has been, and I'm not sure when this started, but a podcast with Jorge Cham called Daniel and Jorge Explain the Universe, which is from iHeartRadio, right?
Yeah, it started out with How Stuff Works, which was then bought out by iHeartRadio. And we've been doing it since about last September 2018.
Oh, okay. So pretty recent. And tell us what you do on that show.
That's a lot of fun. It's me and Jorge, and we just talk about a question in science. So we take on some big, hard to wrap your mind around question that we think people are interested in, but it's difficult to find a satisfying answer via Google. What is dark energy? You Google that, you get a lot of really detailed technical stuff. And so we just talk about it in a way we hope is accessible and fun. And I play the role of the expert. I'm there to make sure we know what we're talking about. And Jorge has a real gift for translating academic thought into accessible, understandable phrases. And so he keeps me honest. He's like, well, hold on a second. What is that word you're using? What does that really mean? Or you're saying this and I'm understanding that. Are those two things really connected? And so we try to just break down big questions about the universe into an accessible format. And we also get into technology stuff. Like yesterday, we recorded an episode about can you sail from star to star on solar sails, stuff like that.
For those who don't know, Jorge Cham is the author of a great series called, I call it PhD Comics, Pilot Higher and Deeper Comics. He's been doing that since his grad school days at Stanford. And for those of you who are in undergrad or graduate school and aren't familiar with this, we'll put a link in the show notes. But, it's just a commentary on academia and science and graduate school and et cetera. It's really worth your time. Something else that you, I guess, did ahead of the podcast was you wrote a book with Jorge. It's called We Have No Idea, A Guide to the Unknown Universe, which based on this conversation sounds right up your alley.
Yeah.
And so what's that book about?
That's a book where we try to take big questions in science and tell people what we don't know. We felt like there's a lot of great science communication out there, and a lot of it is focused on describing to people what science has learned, which is great because science has learned a lot of amazing, awesome stuff. But we felt like sometimes if you're the kind of person who reads the science section in the New York Times, you'll hear about a discovery and it's like, oh, this is an amazing thing we learned, but you didn't even know that the question was being asked yet. So we wanted to make sure people understood what is the edge of our knowledge? What are the questions scientists are asking? What don't we know? And so we decided to write a book about all the things we don't know about the universe instead of all the things we did know. And that was really fun. And that came out in 2017. And again, I served the role of the expert, so I typically wrote the first drafts, and then Jorge went through and made sure it was accessible and understandable, and actually this, let's start with this concept instead of that concept. Plus, maybe the best part of the book is that he drew maybe 400 little diagrams and figures and jokes that went into the book that really help keep the mood light and make it more accessible and also illustrate some of the concepts. Figures are really key. But when I read a science communication book, a popular science book, and I see figures that clearly have been drawn by a scientist using Photoshop or whatever. PowerPoint.
Yeah.
I'm like, there's something really appealing about seeing something done by somebody who has actual graphic talent. And Jorge is off the charts in terms of his graphic talent abilities. So I think that's a really nice part of the book. And it was a lot of fun. And then after that, we went around and gave a bunch of lectures and met people. And that's sort of where the podcast was born, is out of that book tour.
How did you and Jorge meet originally?
Like every other collaboration, we met on Tinder.
And I'm sure you can tell me that's true.
No, we predate Tinder, actually. No, it came about more than 10 years ago now. I was thinking about doing science communication. I've always been really interested in it. And I saw somebody else do science communication using comics. It was there's a comic description of how Chrome, the browser, was developed. And I'm not that I'm a programming person, but even still, I'm not that interested in how you write a browser. But this comic was great. It was really interesting. It was fascinating. It got me really interested and explained all this technical stuff in such an accessible way. So I thought, what a great idea. We should use comics to describe physics. But I don't have any artistic talents myself. So I was thinking, who could I get to do these drawings? And I was always a fan of Jorge's, and my wife, who's also an academic, she's a fan. So she said, why don't you email Jorge Cham and get him to do it? I thought, yeah, right. And then I'll email Brad Pitt after that and see if I can get him to do a movie,
yeah, right?
But I just cold emailed Jorge, and he was interested. And so then we started talking, and we did a few videos about dark matter and the Higgs Boson and stuff like that. And one of them went viral. The Higgs Boson one went viral when the Higgs was actually discovered. And we got a lot of positive feedback. People felt like, this is a really clear explanation, and it actually comes from somebody who worked on the project, and that was really cool. And maybe my proudest moment was when the Nobel Prize was announced for the Higgs Boson. Now, of course, I didn't get it, but in the poster that they use to describe the physics of it, they often give a list of if you'd like to know more, it's suggested reading. And our cartoon was on that list. And I thought, oh my gosh, my work has attracted the attention of the Nobel Committee.
Yeah, that's it. Walk out. You're, while you're on top.
Yeah, exactly. Bucket list checked. And so we've been having a lot of fun since then. He and I have a good, creative science cross-mogination. And so we did a bunch of videos together, and then we wrote that book. And then we did this podcast, and we actually have a brand new project that I can tell you about.
Go ahead.
Our new project is a television show for PBS, and it's an animated show for preschoolers, and it's about science, of course, and curiosity, because that's our thing. And the goal of the show is to encourage kids to be curious about the world, to answer their questions. Why are plants green? Why do owls sleep during the day? Why do frogs make those sounds? This kind of stuff that all kids ask. And also to encourage them to use science to answer the questions themselves. So in the show, the kids ask questions, but the adults don't answer them. The kids figure them out themselves. They, take notes and look for patterns and this kind of stuff. And so it's coming out in September 2020, and we're having a lot of fun working on it.
That's really exciting. It's interesting. If I had to guess, I would have personally said that the 5 or 6 to 12-year-old range is when we systematically beat curiosity out of students.
That's when they learn to do worksheets instead of ask questions, right?
Exactly. And they learn that there's a right answer and a wrong answer, and that we must know everything, and that somehow the people that go into science have, later in their careers have done a good enough job repelling that push in most schools. But no, it's great. I mean, I'm 100% on board with the idea that asking questions is critically important.
Yeah, and what we found is that there's almost no science education at the preschool level. And one reason for that, according to my reading of the educational literature, where I'm definitely not an expert, is that preschool teachers don't feel comfortable bringing up science because the kids ask questions that the teachers don't know the answers to.
Oh.
And so often they'll just do a little bit of dinosaurs at the end of the year kind of a thing. And so one thing in our show we're trying to model is showing how the adults don't have to have the answers. Like,
right.
the kids in the show ask a question, the parents are like, I don't know either. How can we figure it out? And our hope is that preschool teachers will watch it and be like, oh, it's okay to bring up a topic and not have an answer to every possible question. That's totally cool. Scientists do that too. And so we want to encourage creativity and curiosity in the young kids and also in the teachers. Yeah,
it's something that I feel is generally a tension, particularly in my area of engineering, or that's what I can speak to, is that engineers are optimizing for a number of constraints, and the optimum is not perfect ever. Yet the way we teach classes is that you'll still get an answer, and that there is an answer when there's usually many answers that are possible in a real situation. So that it's very hard to tell a class like, hey, look, there's gray here. They're like, but my grade is not gray. My grade is A, B, C, or D. So I'm not getting what you're saying.
Yeah, exactly. And there's fuzziness sometimes, and that's okay. Yeah. And that's something we want to teach kids, and we want to have them understand that it's okay that adults don't know the answers to things, and that science is a process, right? It's not just like a list of facts. It's a way to learn about the world, and you can use it yourself to answer your own questions. And that's sort of the high level goal. But then again, we're having fun because, hey, we're making kids television, and that's always a lot of fun.
Yeah. So you have the book, which you wrote a couple years ago. You have this active podcast, now the TV show. You do random podcasts like this one. So, I could ask the question, like, how do you maintain balance? But that, I think, is not a great question in the sense that you're gonna figure out what you need to do among various constraints, and you're passionate about the communication piece, so you make time for it. So I do have a question, and that is, how do your colleagues view this type of outreach and communication work relative to the work you're doing on the more hardcore science side?
Yeah, it's a good question. It depends on which colleagues. There are sort of two camps of people in physics departments these days. There's the people who don't really understand the role of science communication and why scientists should be doing it. And I think they see like, look, you're a professor of physics, you should be doing physics. And anything else you do is not physics, means you're doing less physics than you could be doing. So more physics, please, right? I definitely get some of that. And I get some feedback from even well-meaning colleagues who think, oh, you're doing this now, therefore you're probably not doing research anymore. And I'm maintaining both. I'm doing research and I'm doing these other projects because, as you say, they're fun, they're interesting. So I make time for them. I have time on the weekends or evenings or here and there. I make it all work. But there's also, I think, on the younger side, people who recognize the value of interacting with the community, because in the end, it's the community who's paying for all of this. We want people to understand why science is valuable and important and worth doing and worth listening to. And so it's important that we engage with the public. And so a lot of people in my department are very supportive, and people here on campus are supportive. People outside of physics like that I'm reaching out and trying to connect with people and answer questions. And so I think that there's a lot of positive support as well. And I get a lot of nice feedback from our listeners. I get emails from them. My favorite are like emails from people who say, hey, I listened to this with my 12-year-old who's now fascinated with physics. Or I couldn't answer my 10-year-old's questions, but we listened to your podcast together, and now we get to talk about black holes together. And I think, wow, created a little science moment between a parent and a child. How fun. And that's the goal. It's like, I want to share with people how amazing and wonderful and crazy it is to get to spend your days thinking about huge questions about the universe and the kind of stuff that fascinated me when I was 12, but I didn't have the intellectual framework to really grasp it. I want to give people a way to taste that and enjoy that without having to go through years of calculus and quantum field theory and all that sorts of stuff. So I want to share the juicy bits of this science with them. And it's wonderful when I feel that connection. I can see that I've made a little explosion inside somebody's head. And that makes it all worth it for me. And I think, as academics, our role is not just to teach and to do research, but to encourage intellectualism and scientific thought in the public. And so I'm doing my best to do that. Plus, hey, it's a lot of fun.
And you said earlier, we don't need the calculus. We're just going to mash some constants together until the units work out, right? So you don't even need it. I was going to say that I think it's almost a golden age of science communication, mostly enabled by the internet. This is a theme of mine in general. I'm just fascinated at how, when the cost of a marginal byte is $0, right? One more byte on a podcast or on a website doesn't cost you any more money. There's this explosion of life, right, that can happen that, some people talk about it as part of the long tail, right? With a long tail, there was never time, money, ability to reach people who had diverse and relatively narrower interests in the mainstream, right? But now with the internet, that opens up the long tail, and it creates opportunities for excellent communicators like you or Jorge to fill what has been a void for a long time, I think.
Yeah, exactly. I think you put it really well. And there are definitely people out there who are looking for exactly this kind of thing or exactly that kind of thing. And there's so many interesting podcasts out there. And, a lot of them have small but really devoted followings,
Exactly.
And I think that's wonderful that these communities can connect with the people who want to share these ideas and passions with them. So it's wonderful for everybody.
So we've been talking about communication and outreach to the general public, but I want to talk briefly, or however long we want to talk about it, what the internet makes possible for scientists to communicate with each other. Because for the longest time, right, the currency of science is the paper. And that's how we disseminated our results to the broader community. That's the acceptable form of dissemination. And that's because paper was, from my view, distributable. You could print it, you could distribute it, and that's worked pretty well. I'm not saying it hasn't worked, but with all these new opportunities and because of the change in the cost structure of other forms of media like audio or even video, should the scientific community be thinking about changing or being open to new avenues of communication amongst themselves?
Yeah, I think so. I think that a lot of that stuff is changing pretty quickly. Physics and particle physics especially have often used preprints instead of papers as a way to really communicate, meaning that we take our papers before they're reviewed by a journal and put them on the archive online for anybody to download and look at. And that's really sped up the sort of cycle of communication. You don't need to wait for 3 random reviewers to take 9 months to make comments about the color of your figures before people even get the idea of what you're doing. The idea is already out there, and the journal review process is sort of like vetting and tweaking and improving, but the ideas get out there faster, and that shortens the cycle, because the sooner somebody can hear your idea, the sooner they can build on it and be inspired for the next idea. And so we've really seen, at least in physics, this sort of exponential growth in the intellectual community that comes from a faster sharing of the ideas, absolutely. And inside collaborations, like I work in a collaboration that's 5,000 people, and we have video conference meetings. It certainly wouldn't be possible to do this kind of work without this kind of technology. And we have internal results that have not been shared with people. So those are not papers, right? We have these internal documents that we use in sort of internal conferences we use to discuss with each other. So I think the concept of a paper as a monolith has been broken up, and it sort of more serves as a record. It's like there for posterity or there for you to look something up, and not as much about the actual communication.
Lately, I've been wondering about even mini podcasts, basically around, say, a paper from your own lab, where you're publishing the paper, you put it on an archive or what have you, but then you sit down with, in my community, it's not 100 people collaborating, it's a smaller number, but you sit around the table and walk through the main ideas and maybe talk about what you struggled with and the things that don't normally go into papers but are also quite valuable. But if I'm driving home and want to, get some insight into my colleague's work, or just learn about what my colleague's doing, and I didn't have time during the day, but I do in the car going home. That's, one of the great things about podcasts just broadly, and you could think about translating that to at least learn some about the science that people are doing.
That's a really interesting idea, and I think some of these scientific communities are big enough that they could really benefit from podcasts as sort of internal science communication. That's really cool. I love that idea.
So we'll see. Okay, so Daniel's taken a good chunk of his time to be with us. I want to end with a lightning round, and then we'll wrap up. So I've been asking the last several guests a similar set of questions, mostly fun, and given our conversation so far, I have confidence that this will be a great section of the show. So question 1, what's the most important thing your students or readers or listeners don't know about Daniel Whiteson?
Ooh, something that I'm also willing to share on the podcast, huh?
Correct. That is implied.
My wife's research is also relevant to dark matter because she studies the microbiome of intestinal communities. And so she's always making dark matter jokes, awesome. Which I think you can connect the dots yourself.
Okay. Well, yeah, we'll let people do that for themselves. Question 2, who were some of your early mentors?
Well, that's a great question. That's a bit tricky. I actually struggled a little bit in my career looking for mentors because I saw a lot of folks who were 10 or 15 years older than me leading lives that I didn't know that I wanted myself. People who were like slavishly devoted to their science at the expense of their families. A lot of the tenured faculty I knew when I was a grad student were on their second or third marriage. So it was difficult for me, frankly, to find somebody who's leading a path that I could follow. So I never really had a lot of great mentors. I think postdocs served as good mentors for me. There was a guy named Marumi Kado who really showed me how to think for myself and ask my own questions and not be afraid to follow the answers. And another postdoc, Ella Barberis, who showed me how to balance life and research and mental health.
So other than your own, what are some of your favorite books, blogs, or podcasts?
I really enjoyed Max Tegmark's book called Our Mathematical Universe, a really interesting deep dive into how do you construct a universe like this? What does it mean that the universe can be described mathematically? I think he goes a little too far in his philosophy, but I thought it was well written. It was interesting. It was a fascinating read. That's one of my favorites. I mostly read science fiction, and so I like space opera. So I like Alastair Reynolds, and that's really fun because Alastair Reynolds is a great science fiction writer, but he's originally an astrophysicist. So he started as a researcher and had a bunch of ideas for novels and then started writing them. So to me, that's inspirational to see somebody cross over from one very highly specialized field into another and be a success in both.
I'm going to feign ignorance here. What is space opera?
Oh, space opera is science fiction that is written across vast distance scales, vast time scales, 1,000-year empires and, galaxy spanning plots. And, Star Wars, for example, is a space opera.
What's something you're excited about right now?
I'm really excited to be working on this television show for PBS. I'm learning so much about how television is made and how it's funded and how the educational principles get folded in. I learn something new every day. And for me, it's all about learning and trying things new. I never want to be doing the same thing one year that I was doing before because then I get bored. And so it's been a really exciting adventure so far.
Yeah, I'm looking forward to that show coming out. So tell us about a time when you failed and what you learned from that experience. Oh, folks, he's never failed.
That's a great question. I had a project with some friends when I was a postdoc, and we were good friends. And then we tried collaborating together, and the science and the friendship didn't really quite mix very well. And the science fell apart, and then the friendship fell apart, and so I lost a friend and a lot of time, and that was kind of sad. And so what I learned from that is that you can have different kinds of interactions. You can have people who you're good friends with, and even if they're scientists, doesn't mean that you're necessarily going to be able to collaborate with them. And vice versa. Some people you can collaborate with, and you don't necessarily have to also be able to have a beer with them after work.
Right. So other than your book, blogs, and podcasts, and all the things you're doing, television, what else do you do for fun?
I'm an avid amateur baker. So I love baking breads and desserts and all sorts of stuff like that. I love the Great British Bake Show, and together with some friends nearby, we often challenge each other, like, hey, can we try to make this crazy thing we saw them make on the show? So I love the sort of food chemistry of baking. Also a big camper, so I love going into the outdoors, enjoy looking up at the stars at night, but also just being out in nature and enjoying the quiet and the rhythms of the forest.
So your favorite, I'm not sure it's your favorite, but you talked about the chocolate babka.
Yeah, that's right.
On that People Behind the Science podcast you were on. We'll put a link in the show notes. Great descriptions of the food or the results, the positive results and the negative results of chocolate babka engineering, basically.
You're trying to bring an old Jewish food into the modern day. Yeah, exactly.
We're going to mainstream chocolate babka, people.
Exactly.
Okay, so a college student comes up to you saying they're interested in a scientific career. What advice would you give them?
I'd say get some experience, because a scientific career in research is very different from the experience of being a science major in college, which is mostly doing homework. Research is very different. It can be thrilling. It can also be really boring. And there's not a very strong correlation between time spent and progress made. And so I really encourage them to discover for themselves whether it really suits them. And the only way to do that is to have some experience. I tried lots of different fields of science before I discovered particle physics, because you have to find one where you're interested in the big questions and you also actually enjoy the day-to-day work, which can be totally disconnected. It could be programming, it could be building things, it could be designing things. And so you really have to find where you fit. And so I would say get some experience. And I really encourage all the majors here at UCI, the physics majors, to get research experience as soon as they can.
I'm reading a book called Range by David Epstein, which his main thesis is that people who have a bit broader experience and tried a bunch of things, either because of those experiences or they found the thing that works well for them as individuals, ultimately can do quite well relative to folks who kind of stayed on the narrow path and did one thing. So I'll put a link in the show notes to that book, but I agree with that advice. So last question, and then we'll let you go. What do you know now about science that you wish you knew 20 years ago?
Wow, that is a great question. 20 years ago, I didn't realize how much of science, how much of good science, is really driven by the individual questions of scientists. I think I thought of it more top-down, like we as a species have decided to look at this and that and the other. But really, progress is made when people are curious and they're like, I want to know the answer to this. And I've seen this in my students as well, that the ones that succeed are the ones that are answering their own questions, the questions that they think about when they're running or when they're watching TV or in the shower or whatever. And they get ideas for it. So I didn't realize when I was younger that science really is about following your own curiosity and trying to figure out for yourself what is it you'd like to learn about the universe.
Well, Daniel Whiteson, thanks for coming on the show. This has really been great.
It's been a pleasure. Thank you so much for having me on, and thanks to your listeners for their patience with my bad jokes.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.